very first point, not even talking about it, I'm not endorsing anything today. I will be showing demos from different products that I think are relevant to the sensor that we're discussing, but it's not necessarily any sort of endorsement. I might not have even ever played with the sensor myself. So with that being said, this is also not a presentation about the far future of sensors. We're not talking about sensors that are only seen in academia, in the most prestigious labs. These are things that you could theoretically buy online today, right? And source them from, if not necessarily a big box store, like Amazon maybe, or the manufacturer's website. So nothing, everything is accessible to us, but it's just not used in robotics. And that's the question today, is like, why aren't these things used in autonomy? Why are they still relegated to the future? Right. And so this is what we're going to be digging in today. So first off, to kind of level set the field here, we need to have a baseline of how to evaluate sensors. The way I do this, and when I see a sensor, is have four things: technical qualifications. There's range, which is the observation distance. There's environmental robustness, which is basically the ability to operate in whatever environment you're in. Of course, autonomy has one of the highest thresholds of environmental differences that they have to operate in. It's very important. Fidelity is the detail of observations for these sensors. So what is the granularity of observation, or how fine are these things in space or time? And then the field of view of the sensor is pretty straightforward. How many, out of my Euclidean space, how much of that can I see at once? So with these things in mind, let's go to the most common sensors in autonomy in my mind. They're the camera, depth sensor, and LiDAR. And if we evaluate them across these metrics, no one of these sensors does better than any other. So you can see that cameras are pretty environmentally robust, but their field of view is pretty narrow generally. It's a camera, 90 degrees maybe. The range is also not great because you have a certain pixel size that not only gives you a certain fidelity and range. Depth, you can get a little bit better, but that's stereo now usually, or synthesized time of flight. So range can be hindered and actually gets, the accuracy gets worse as you go. Fidelity is pretty good. But field of view, environment robustness, these things kind of compensate. LiDAR, of course, has great range. Its fidelity is okay. If you have 16 beam or 32 beam LiDAR, it gets a little questionable. These things are getting better. But really, you never see any one of these individually in autonomy. They're always together, right? This is why they're called the common sensors. And the reason is because they compensate for one another naturally. However, we'll notice that there's still a lot of room to improve. So you can put a camera and a depth and a LiDAR sensor on a platform, but at the end of the day, there's still going to be things that you could do better, right? And so our job today is to fill in those gaps. Even though we have the common sensors and we have played them to the max, how can we make our sensor system better? And this is where the future of sensors comes in. So to start with, let's go with, one of the coolest sensor modalities, I think, on the market right now, millimeter wave. So usual millimeter wave has frequencies from 30 to 300 gigahertz, which means you have a 1 to 10 millimeter wavelength, hence giving you millimeter wave. This fidelity, like this small wavelength, actually makes greater fidelity in the signal. So you actually get a much sharper signal on the return. It has strength similar to other radar, all day, all weather sensing capabilities, very little atmospheric interference. You can see through fog. Small form factor, because literally to make those small waves, you have to pack everything onto a smaller chip. This is also already used in ADAS and AV. So, it is used as an augmentation to traditional radar and LiDAR systems. And millimeter wave radar can create a tire map on its own. So you can do some really tricky things with multiple radar sensors to actually create a full map. So this is an example I took from a company called Zadar. Again, not endorsing anything, but here's their comparison of a digital LiDAR to their Z prime multi millimeter wave kind of fusion system. So you can see that despite them being different modalities, you get near same fidelity, range, field of view as a traditional LiDAR. And this just gets better as your radar algorithms hone themselves, which is really cool to see. So if we look at our comparison chart, our evaluation of a sensor, range is great. You can, fidelity is also great. So millimeter wave radar compensates for a lot of the things that LiDAR can't due to environmental conditions, which means environmental robustness also goes up. Field of view is limited to how many you can pack onto your thing. So I rated it a 5 here, but that goes up, with the smarter your algorithms are for filtering. So millimeter wave is really cool. And it is gaining traction, but I would still consider it way out of the range of, most projects. Event camera is the second one I want to highlight. I actually just wrote a post about this on the Tangram Vision blog, so you can go check that out if you'd like. But event cameras are really interesting things. So instead of having a pixel array that takes the magnitude of your scene, it instead has every pixel as its own initial sensor, and every pixel takes the change in brightness of that segment of the scene. So it's like a huge array of sensors onto a camera field. It only registers 3 things: a pixel gain in brightness, loss in brightness, or no change, which means that the event camera data is basically a fluctuating field of different changes in magnitude. The cool thing about having every pixel being its own sensor is that every change in that pixel's value is sent instantaneously over the wire. So, FPS doesn't really make sense in this context. Instead, you get over, 1 million events, 2 million events, 12 million events, 1,200 million events, depending on the size of your camera. And as soon as the event triggers, it goes. So event cameras give you a lot in terms of data bandwidth, data speed. It also has a huge dynamic range, which means that even in the darkest conditions and lightest conditions, it will work, because it's not giving you a magnitude of the brightness, it's giving you the change in brightness. So just that little shift in sensor operation allows for all these things. So here's picture of a racer running horse with an event camera. You can see that the edges of the scene are pretty sharp. So as the horse moves, you can see very distinct black lines, white lines, depending on how that pixel changed over time. And this is all you get with event cameras, but you get a lot of it. And so if you can use it the right way, you can basically do real-time odometry, object detection, things like that. Very cool stuff. Event cameras on our graph just max out environmental robustness. You really can't do better when working with light. Its range, field of view, and fidelity are all restricted because of its camera form factor. It's still a field of pixels. But if you want something that will just work as far as the signals it gives you, you really can't do better. Thermal cameras are the next modality I'd like to highlight. You're probably already familiar with thermal cameras. They give you IR readings. Really, their advantage over other cameras in terms of autonomy is that you can see things that are living, that are changing their heat gradient. So this can be a person, this can be an idling car, anything that you can think of that you might want to know has a state of change. For thermal, this works, right? And they have amazing fidelity. They, sensitivity to a few millicelsius usually, and they go from the coldest to the hottest temperatures that you could see in an environment, right? They're a great supplement for LiDAR and radar because they give you a little bit more information that even a visible camera couldn't do in important live scenarios. So, and it has, unique features. They're thermal. It's less prone to false positives. You're not going to get glare or anything because it's just a thermal camera. So when we look at that gradient, you'll see it's okay. It's really highlighting a different modality So its real advantage is that it gives you a different sort of visual information, not necessarily just what's in your scene, but the way it's reacting to heat. So on paper, it doesn't look very interesting, but it does compensate for a lot of autonomous operations pretty solidly. So then the last one I want to talk about, omnidirectional vision and range. Again, some of you are already probably familiar with this, but the coolest thing about omnidirectional is that there's no need for camera stitching or post-processing. You get the entire scene for free. Your field of view is maxed out. You can't do better. It's 360-degree horizontal, usually 180-degree vertical, probably more, depending on how it's mounted. And the range of your scene can also be derived through clever time of flight tricks or stitching tricks. So like the way no matter how you put this camera together, you can get some really cool information from your scene. So here's an example from a company called DreamView. So you can see on the bottom, DreamView actually creates a 360-degree range camera. So you can see both the visible and the range data. And on top is the Tangram Vision depth sensor visualizer of the DreamView's field of view. And you can see that it basically goes all the way up and down and then 360 degrees around. So pretty powerful stuff. DreamView, I don't think, is the only company doing this, but its impact on sensors being you don't have to do any post or pre-processing to get as much data as you would like about the visible scene. Again, looking at our chart, field of view maxed out, really can't do better. Range, environmental robustness, and fidelity are all pretty good, but as you can see, for depth visualization, there's a little bit of synthesizing that needs to occur for it to really get up to spec. If you're looking for visible data, really not a big deal. You're going to get, good stuff. So with all that being said, this is what could be if we just used all these other sensors. They don't have to be relegated to the future. We could just put them on now and then have range, field of view, environmental robustness all maxed out, and our fidelity be pretty good, right? So why aren't these interesting and novel sensors being used on developments today? The answer is, and you probably saw this coming, is that I'm lying to you. Not in that the technical metrics that we've gone over are wrong. They're very right, and I hold to them, but that's not the full picture. And a quick survey of some YouTube comments on these big sensor reveals kind of says it all. So like the first is, so how to fusion? Like if I have this, how do I use it? On one TI video, I think they were releasing radar or something. It was like, very nice TI, we will buy it as long as the price is right. Right. I don't want to buy a $4,000 sensor if I know it's not going to be useful for my project. I want to connect ARW1.3 with the T to radar signal processing. Can you please let me know how to directly connect these two EMs? Like, how do I make these things work together? Have you done biological safety tests? What is it going to do to my sex plans? These are all very important questions that are not answered by our previous metrics, right? So how do we abstract these away, and what is really preventing us from using these? It's commercial factors, right? That's it. Our cost, got to keep that bill of materials down if we're going to go into production. Engineering ease. How can I, if I gave this sensor to my engineering team, would they be able to use it? Would they be able to integrate it? How long would it take to get something up and running? Proven business case. Are other companies using these? This, I think, is one of the most overlooked questions in any sort of hardware. Like, is it proven in the field? And if not, why? And then manufacturer reliability. Are sensor companies making these devices in reliable quantities? And this goes for everything, not just these unique sensors, but you can think of the Intel RealSense line that has been heavily modified, not canceled, but that was a huge deal in the sensor community last year. Is like, is this end of life? What do I do? I pick on Intel RealSense a lot for this, but they're by and far not the only ones who do this, right? So really, you need to know, if I put this on my platform, am I going to buy more if I find success? So let's now go over these factors given our common sensors, right? So you can see camera, depth, LiDAR. We still have our 4 technical qualifications, but beyond that, we now have these commercial qualifications. And you can see that now we see why we use these common sensors. Camera and depth have engineering ease and business case locked down. Cameras for sure, cost, manufacturing, business case, engineering ease, everything top notch. I mean, you can find cameras everywhere. LiDAR business case, much higher than something else we would see elsewhere. Cost of manufacturing are getting better every day, especially as LiDAR enters the automotive industry. And so, with this fuller picture, we now see there's much more to think about. Before we understood that there were gaps in our technical, but now if we look at the big picture, we're like, we really can't do better than these 3 sensors for a holistic view of our platform. So let's go back to our, obscure sensors that had hopes for technical prowess and see how they do. Millimeter wave radar, we highlighted their technical capabilities, pretty impressive. But now when you compare them to our commercial capabilities, we find that they're sorely lacking, right? There's serious effort to build millimeter wave radar. A lot goes into it, and it goes into a very small form factor, which is really cool. It's an engineering marvel. And if you see these things work, it's very impressive. But there's a lot that goes into making that signal work. There's a lot of pre-processing steps. There's a lot of filtering steps. And vendors of these systems are probably struggling with integration just as much as you would because of the way that these things go into the platform. So I've seen, Zadar, which is the company we talked about before, their radar integration isn't just giving you the radar, it's the entire platform, because they know how to use their radar the best, and they want to convey that information to you in as little trouble as possible. And that's a really common way to interact with millimeter wave. So not just get the raw data, but get it through an interface or get it through a hardware system, because of the complexity, right? And so when you go to engineering ease and cost, it might be easy then when you're in their network, in their software, but extending it to your platform could be a pain in the headache. So things to improve here. Event cameras. Of course, they were the best environmental robustness. I think event cameras are so cool, but admittedly, they are not easy to work with. And there are a few reasons why. So first off, there are no less than 8 common ways of packaging event camera data. Because it's time independent and space independent, you have this huge matrix of values, millions of them over the space of a few milliseconds, really. And you're trying to compress that down as you go into something useful for your algorithm. Well, finding what's useful for your algorithm can probably take some time. And unless you're very familiar with event cameras and kind of their advantages, it's going to be hard to integrate that in. Also, all you get is the sign of the brightness change. So if you're used to thinking as images as magnitude, you're in for a rude awakening. Again, this seems like a small shift, but it really does change the way everything works, even if you synthesize images. And there's a serious trade-off between resolution, exposure, and data throughput at the hardware level. So if you get the not necessarily wrong hardware, but different hardware, you'll have a lot more events. You'll probably have to change your exposure, even to the point where things fade out, to control that event rate. And even then, you might not be getting the data you want because it's just getting so saturated. Going the other way, having a smaller resolution camera, you actually have just less data. And you might be able to control the throughput of your events so that you can handle it in real time, but you're just getting QVGA information. There is some research indicating that this is not a big deal, that if you're familiar with event data, QVGA or smaller resolutions can be fine for your needs. But I think that remains to be seen, especially because event cameras are still in such a development stage. So lots of pros and cons, especially when you get to the nitty-gritty of actually putting it in and engineering with it. Thermal cameras. As I said before, thermal cameras didn't really seem like they did a lot, but it's because they're a whole different way of looking at a scene altogether. So really they're supplementary. They should be supplementary. But that's not always the case, right? There are a lot of thermal camera manufacturers, but cost can be a factor. They're kind of expensive. And once you find that expensive thermal camera to put on, there's not a lot of off-the-shelf software for sensor fusion. So this modality that's really meant to be a supplement to other modalities often ends up just working on its own, just getting the thermal data and trying to work with the thermal data on its own. When in reality, it's a much more powerful modality when you combine it with everything else on the system, right? And to this point, thermal, in my anecdotal experience, has really just started to be considered a supplement to other sensors. So it will take engineering teams who already have the sensor package they want to integrate in the thermal as a supplement afterwards. Yeah, and then again, images are very low resolution. So once you get all that sensor flow going, you're still only be using so much data, which means that if you want to use it maximally, again, you'll have to fuse it with probably something more detailed. Yeah, so it's a pity that in most instances that I've seen, and this could be wrong totally from numbers, but thermal cameras just work in isolation. And then the last one, omnidirectional vision and range. Why use one camera when three can do the job? So cameras, conventional cameras, as we saw before in this slide, conventional cameras have, the best commercial metrics of any sensor ever, because they're just so incredibly cheap. So if you had three very cheap cameras that you could stitch together into a 360-degree field of view camera image, why would you pay for the omnidirectional sensor? And I think this is probably just the biggest hang up for omnidirectional vision. Omnidirectional images require some specialty knowledge to even understand the data because they have such a warped field of view. You need different models, you need different calibration techniques. The data streams aren't intuitive, although they can be broken up to be built as such. So really, the data itself suffers from the same problems cameras do, except you have more complexity. So when it comes to having an omnidirectional camera or just stitching together a couple of cameras to get omnidirectional vision, I think many engineers would start with the latter. Whether or not they end with the latter, I think it's different. I have seen some platforms put on omnidirectional vision or close to it to great effect. And you also have companies trying to extend omnidirectional vision capabilities like DreamView and their range, right? So there are cool things coming out of this pipeline, but for now, while the stitching is cheap, I think at least cameras have an uphill battle for this. Omnidirectional cameras have an uphill battle to get integrated. So where does that leave us? I mean, if we look at our 4 future sensors, our obscure sensors, we'll find that, again, they did compensate really well for one another in the technical realm. And they have some very powerful techniques at their disposal. But once you get into the commercial value of adding one of these to your platform, the ease goes down quite a bit. And so we're left with this really cool technology that no one's willing to jump in and integrate. And so this is our job tomorrow, our job being our job as engineers in the robotics and autonomous fields. More specifically, also Tangram Visions' job as sensor advocates and sensor software providers are basically make these sensors better in every way. So they have amazing capabilities. They're not off the shelf. You have to do a little engineering with it. But if all these engineering, business case, manufacturing cost could improve, then we could see vastly different platforms coming out in the future with some really cool capabilities that haven't been unlocked with the conventional sensors of today, right? So that's what I'm excited for. That's what I'm pushing for. And series like, Sensoria Obscura and evaluations of different sensor systems by Tangram are just trying to further this so that these things are accessible not only to those who can afford it or those who have the knowledge, but anybody who's interested in the field. So really, that's my shtick. Thanks for listening. And of course, we're going to take questions afterwards if you have them. I want to mention that our next webinar is actually going to be on troubleshooting calibration. That's a working title, but it will be calibration centric, as that's one of Tangram's specialties. We've scheduled it for Wednesday, January 25th, 10 to 10:45 Pacific time. Jeremy Stewart, one of our senior perception architects, is going to give that, and I'm sure it'll be pretty good. Very excited for it. At the end of this presentation, I've also put some resources, selfishly, as Tangram CEO. Sensoria Obscura blog series. We've been labeling these so that they're easy to find. Just go to Sensoria Obscura categories of the Tangram Vision blog, and they'll pop up. We plan to add, so right now we have event cameras, thermal cameras done. We'll be adding omnidirectional, millimeter wave, and several other modalities in the coming months, trying to make this a full compendium of resources as well as information about these obscure future cool sensors. And then we have the depth sensor visualizer that I demoed earlier this talk. You can just compare sensor ranges and field of view. So if you're looking for the capabilities of different depth sensors, that might be a place to start. You know, again, a helpful tool that we've tried to put together for the community. Yeah, so that's it. Thank you very much.